We are trying to analyze the forces acting on the book. Let's start with our step one. Is this a first law problem or a second law problem? How do we know it's a first law problem? That's right, book's at rest. So net force equals 0. That's how we start our problem. Next, we're going to draw a free body diagram. The idea of the free body diagram is to help us isolate forces and what direction they act. So I start a free body diagram by taking my book and reducing it to a dot. Now we're just going to try and identify the forces that are acting on the book. All right, the book is the object in this problem. So I'll start by going through a list of forces that would probably be a useful list. For example, is gravity acting on the book? Most certainly. So I draw a downwards arrow to represent gravity acting on the book. When I draw this arrow, I am kind of establishing the scale of my problem. So what I mean by that is the size of the other arrows I'm going to draw largely will be based on the first arrow that you draw. So we know the system's going to be in balance. It's not in balance right now with what I've drawn, but I understand that the other arrows should be complementary to this one. Now it's not complete unless you label it. You have choices. I'm going to use a capital W. Now we're going to start going through our contact forces. Is there any surface in contact with the book? Yes. Name one. The board. The board is applying a force to the book. Now, when you draw a normal force, by definition, normal forces must be perpendicular to the surface in contact. Now, the only way the board can apply a force to the book that is perpendicular to the board is if it's applied this direction. Correct? That is a perpendicular force perpendicular to the board. So, now subscripts are going to become useful here because you may have more than one normal force, or more than one tension force, or more than one frictional force. So finding a way to differentiate one normal force from the other is a good idea. I put a little W there, saying this is a normal force from the wall. Is there any other surface in contact with the book? The hand. Is it clear that the hand is applying a force that is perpendicular to the hand? Now, I'm going to try and draw this in a way that is complementary. I know the book isn't accelerating into the wall, and I know the book isn't accelerating away from the wall, so I want these to demonstrate a certain amount of balance. So I'm going to draw a force that appears to balance the normal force from the wall. And we said that this is a normal force, so I'm going to say normal force from my hand. Do these appear balanced? It looks balanced left to right, doesn't yet look balanced up and down, but we haven't exhausted our list of forces yet. Is there any cables, ropes, or anything like that that is connected to the book? No, so there's probably no tension forces acting on the book. So let's go through our resistive forces. Is there any likely resistive forces acting on the book? Go ahead. I think there is a frictional force acting on the book. I think that makes reasonable sense. By definition, friction is a force that tries to prevent one surface from sliding past another. I think that there's a frictional force preventing the book from sliding down the wall. So how would I draw this frictional force? Yeah, frictional forces are always going to be parallel to the surfaces in which they act, because they are preventing the sliding of one thing past another, so they will always be parallel to the surface. Now, if you guys are trying to take notes, a frictional force is parallel to the surface. A normal force is perpendicular to the surface, so it appears as though friction and normal will always be perpendicular to each other. Does that make sense? Right? If the normal force is perpendicular to the surface, and the frictional force is parallel to the surface, the frictional force will always have to be perpendicular to the normal force. Now, if you're really paying close attention, I don't think there can be a frictional force without a normal force. If a frictional force is caused by one surface trying to slide past another, there has to be surfaces in contact. Normal forces, by definition, are surfaces in contact. So there's no friction without normal force. If you have a situation in which there's no normal force, there won't be a frictional force. Does that make sense? We're going to see some examples of situations where there's no normal force, so there won't be a frictional force. I don't have to worry about it. But in this case, we have a surface in contact, the wall, and maybe my hand. However, I'm just going to draw one upward force. And again, not arbitrary. I'm trying to draw this upward force to balance the weight because I know the book doesn't slide down the wall or accelerate down the wall. So, and as you said, it's not just any frictional force, it's the static frictional force because it's a situation in which a surface is not moving with respect to the other surface. So that's static friction. I'll put an S there to remind me. We deal with static friction different than we deal with kinetic friction. We haven't learned that yet, but we will. Air resistance can only happen if an object is moving, and I said we're not going to have any air resistance problems for a while, so I think we're good to move on to the next part of this. So we've identified all the forces acting on the object. Next step after I've identified all the forces acting in the system is to recognize that our free body diagram is essentially done. If you were asked to draw a free body diagram, you would end here. But if you need to do work with your free body diagram, then you will go to the next steps. So for the most part, the next steps are necessary to establish what you have with your problem. So we're going to move on. Go ahead.
Wouldn't you have to label your coordinates or like, not coordinates, but like
That's next.
positive x?
3 coordinate system, resolution of vectors. So that's exactly what we're going to do next. So this one is kind of ridiculous, and I'm starting with ridiculous examples on purpose. Like I want examples that are accessible to everybody on purpose. But it's still a good exercise to recognize your next step is going to be drawing in a coordinate system. Now I'm drawing this to the side because I have reasons I want you to see. So just give me a moment. When you apply your coordinate system, the truth is you can apply a coordinate system in any direction you would like to apply it. But you want to choose to apply your coordinate system in a useful manner. And I gave you 2 priorities yesterday. Either line up one of your directions with the acceleration or attempt to line it up with as many forces as possible. Now this system isn't accelerating, so it makes perfect sense to line it up with all the forces. But keep in mind, we're starting with the simple questions. The harder ones are coming. But yeah, it's at this point that you start labeling. I'm going to do positive y, positive x, negative y, negative x. I've identified a coordinate system that can be used to help us solve this problem. Are there any vectors that are off axis? If there's an off axis vector, you have to resolve it into components. If there isn't, you can move on. I see no off axis vectors, so we're going to move on to our next step, which is apply Newton's laws. When it comes to applying Newton's laws, you take whatever you decided and you apply it in both the x direction and the y direction. If it was accelerating, one of those will have ma for the direction of the acceleration. If it's not accelerating, then both of them get 0. So net force in the x direction equals 0. Net force in the y direction equals 0. Now, I'll remind you, this isn't an equation. This is a set of instructions. And because it's a set of instructions, you follow the instructions. The instructions say to add up all the vectors in the x direction, taking into account their direction, and set them equal to 0. There are 2 vectors in the x direction, the normal force from my hand and the normal force from the wall. I've identified the direction of the wall as being the negative direction. I'll add them up and set them equal to 0. Similarly, in the y direction, I have 2 vectors. I have the frictional force in the positive y direction. I have the weight in the negative y direction. So I will make the weight negative and the frictional force positive. I will sum them and set them equal to 0. So what I have done now is I've generated 2 relationships that, depending on my situation, could be used to solve whatever our question is. Now, I ask no question. We are just analyzing a problem right now. We're going to start answering questions after a couple of examples. I just want to step you through the process, step you through the procedure. Ready for our next one? This is our next one. The calculator is our object. So I have the calculator on top of the book. I've opened the book to some angle theta. That make sense? Is it clear from your vantage point that the calculator is not moving with respect to the book? So what do you think? First law problem or second law problem?
First law.
I think this is the first law problem. If I was to draw this question, I'd probably start up with the calculator. And then we have our book. And to be honest, it's pretty amazing how sticky those feet of those calculators are. There. Is that what you guys saw? All right. So we've identified that the calculator is at rest with respect to the book, but the book cover has been open a certain amount theta. And you guys all said that the net force in our system is equal to 0 because the calculator was at rest with respect to the book. All right. We've done step 1, which is identify if it's a first law problem or a second law problem. So we're moving on to step 2, which is to draw a free body diagram. So I think you need less help each time, so I feel as though I don't need to help you here. You have a set of rules. Please apply the set of rules to the calculator. I'm going to start at the top. Which force should I start with here? Gravity. Gravity is drawn as a vector towards the center of the Earth. You don't get a choice here. So what direction does that arrow have to be drawn? Down. So all of you who drew it at an angle, fix it. Force of gravity is straight down. And I don't know why you changed it, because you knew the first time we did it, straight down. So that's our weight. Is there any surface in contact with the book? Okay, you don't get a choice on how to draw this. If there's a surface in contact with the book, then you have to draw a normal force that is perpendicular to the book. Now, it's not arbitrary. Perpendicular to the book can only be drawn one way. Is that perpendicular to the book? It's the only way this can be drawn. So fix it. Because a bunch of you have it drawn weird. Some of you have it drawn it perfectly sideways, but that can't be. The normal force must be perpendicular to the surface in contact. Does this look balanced? No, so this can't be it, because I should have another force here to help bring this into balance, maybe more than one. Is there any cable, rope, or something connected to the calculator? No, so there's no tension force here. So I don't have to worry about tension. Is there one surface attempting to slide across another? Yeah, I think there's friction holding the calculator in place. By definition, friction is a force that tries to prevent one surface from sliding past another and has to be parallel to the surfaces in contact, which means my frictional force can either be this way or this way. Which one of those makes the most sense? Force number 1 or force number 2? Force number 2. I think if it was force number 1, the calculator would be accelerating. Those wouldn't be balanced. So we're going to choose a situation that tries to bring the system into balance. And friction is trying to prevent it from sliding down the ramp. So yeah, I think our frictional force is going to be this way. That's perpendicular to the normal force, parallel to the surface, and because it's not moving, this is static friction. All right, we have drawn a free body diagram that demonstrates what I think looks like balance and also shows the forces that are acting on the calculator. Your next job is to apply a coordinate system to this arrangement. So I'm going to draw a coordinate system. I've already seen at least one of you make a super terrible mistake with your coordinate system. A coordinate system has to be two lines that are perpendicular to each other. You can't just draw the lines somehow arbitrarily angled. They have to start like this, perpendicular to each other. So I'm going to apply it to my system. There are two priorities here. Priority number one is to align one of the dimensions with the direction of the acceleration. Is the calculator accelerating? No. My next priority is to align it with as many forces as possible. Right now it's aligned with one force. I could stop here, but my next step is going to be to resolve any off-axis forces. And if I leave it like this, two of the forces are off-axis, aren't they? I can choose any coordinate system I want. So it makes more sense to me to turn the coordinate system to line up with the two forces that I know are perpendicular to each other. Normal force and friction are perpendicular to each other. If I line it up like this, only one force is off axis. So it was here before, right? And friction is parallel to the book cover, right? That would suggest that this is theta, right? Because it's parallel to the book cover. But if I want to rotate the axes, is it clear I'm going to rotate the axes and angle theta? Well, that means that this must be theta now, because I moved the axis an angle of theta. So I move the y-axis away from downwards an angle of theta. Look, if you need a note to make sure you never get this wrong, draw a line through the normal force. The angle goes between the weight and the line through the normal force. Every time. Don't get this wrong. When it comes to an inclined plane, the angle is going to go between the weight and the line drawn through the normal force. All right, we can't go forwards until we do a little bit of trig, and the trig is going to be next. We have to take our weight, which is the only off-axis force, and break it up into components. You have done this before. You did it with the planes. So I'm going to take and wrap a triangle around the angle. Remind myself that those two components have to be at a right angle to each other. I'm going to identify that one of these is in the x direction and one of these is in the y direction. And I'm going to apply my trig. The y direction has to be weight cosine theta, because it's the adjacent side. And weight in the x direction has to be weight sine theta, because it's the opposite side. And I've been very clear, you need to make your trig invisible. It needs to be so rudimentary, so practiced, that you can look at a situation and figure out where sine and cosine go. If you're having to stop here and do SOHCAHTOA, it's going to take time, and you're going to lose sight of what the problem's about. But you do have to break up any off-axis vectors into their components. All right, once I've done that, I go down to step 4, which is apply Newton's laws in each dimension. So I will have net force in the x direction equals 0, and net force in the y direction equals 0. I'm going to lay these out. I'm going to go ahead and label positive x, positive y, negative x, negative y. All right, in the x direction, I have what looks like the frictional force is in the positive x direction, and it looks like Wx is in the negative x direction. So that's minus W sine theta. I'm going to set that equal to 0. Any question about those choices? All right, I'm going to go to the y direction now. So in the y direction, it looks like I have normal force in the positive y direction. And it looks like Wy is in the negative y direction. So minus W cosine theta equals 0. I have generated two relationships that could be used to maybe solve something about my problem. Now, we're not quite there yet, but when you do this, you are generating relationships, and we've generated this one, and we've generated this one. We don't know what the question was going to ask, but there could be all sorts of questions here, like what's the maximum angle the book can make it to before the calculator starts to slide? Those are realistic questions. Or how sticky must the feet of the calculator be? But we don't know everything yet about friction and force problems. For example, you're going to be learning that there's a relationship between friction and normal force. This is a future thing. So right now, getting here is just the start. We have other things to apply to these problems. So we're just learning a procedure that can analyze our situation and generate some relationships. All right? We're going to do another example. And this one is one where I think you can get to an answer. So I think this is a good place to try and put more of the onus on you. I want you to imagine I have a sign that I'm going to hang using 2 ropes. The first rope is going to be connected to the sign and the ceiling, like so. And this makes an angle of 40 degrees with the vertical. The other rope is going to be perfectly horizontal. And this gets attached to the wall. The sign has a weight of 200 newtons. I'd like to figure out the tension in each cable. That way, when I buy the cables I'm going to use to hold my sign, I make sure that they can hold the sign without breaking. Everyone understand the parameters here? We're looking for the value of T1 and T2. Newton's laws can find the size of forces. Let's do so. To do this problem, you'll have to decide at the start, is this a first law problem or a second law problem? This is a first law problem, certainly. So if you would please, draw a free body diagram that could support solving this problem. All right, can I assume we are to a point where we've at least drawn a force? Do you have a question? I think it would just be a tension force. So I'm going to start with a downwards arrow to represent the weight of the sign. And we know this to be 200 newtons. All right? What else should I draw? Go ahead.
You should draw a rope going to the top left of that.
Okay. Something like that. Now here's the thing. I'm eyeballing it because I have to make sure I'm drawing something appropriate, but I know that tension 2 does not pull up on the box at all. So I know that this tension 1, this portion of it, has to be 200 newtons, right? Because that's the only rope that's pulling upwards on the box. So as I draw it, just the upward part has to be 200 newtons. So I'm drawing it to be longer than the downward force, intentionally to try and make sure it looks like it's balanced. And I'm going to label this T1. Anything else? Go ahead.
T2 is pulling the sine perpendicular to the bottom arrow
Okay. This way?
on the right side.
Okay. So that way?
Yeah.
All right. Again, intentionality. It's got to be at least that big, right? So I'm going to draw this as T2. Is any surface sliding past another surface? No. I think we're done. Right? I see no surfaces in contact or anything like that, so we have drawn all the forces that I think are acting on the sign. So my next job is to come up with a coordinate system that I could apply on top of this. I'm going to just draw a coordinate system and kind of think about how I want to place this coordinate system for this problem. So if I place it like this, I'm already lined up with two of the forces. So I don't see any reason to rotate it. Do you guys? Because if I do rotate it, then that means I'd have to resolve two forces. If I do this, I'd have to resolve two forces, and that seems like more work. So I'm going to leave it here, and that way I only have to resolve one force. I'm going to label this the positive y, and this the positive x. And I'm also going to note that we were given this angle as 40 degrees. All right, so in order to solve the problem, I have to take my one off-axis force and break it up into components. So I'm going to draw a couple of components by wrapping them around the angle. All good so far? These have to be at a right angle to each other. And it seems to me that this one is going to be T1 cosine 40. And this one is going to be T1 sine 40. Right? The top one is going to be the opposite side, so we get sine. And the one along the y is along the y-axis, so it's going to be cosine. It's the adjacent side. I've broken all my forces up into their components. I can go on to step 4 and apply Newton's laws in each direction. So net force in the x direction, that's going to be T2 minus T1 sine 40 equals 0. Any question about that? All righty. Let's go to the net force in the y direction. Add up all the forces, taking into account their direction, set them equal to 0. I see T1 cosine 40 upwards, this one right here. And I see 200 downwards. And they have to sum to be equal to 0. Again, the force concept model generates relationships that could be used to solve our problem. You were asked to find the tension in the cables. Will either of these give you a pathway to find the tension in the cable? Yeah, I think so. I think this one has one unknown in it. I think I could use it to find a tension in the cable. And once I do, I could probably use that up here to find the other tension in the other cable. Seems like a reasonable plan of attack. This is outside our set of steps, understand. The force concept model generates the relationships. It does not solve the problem. If you have a problem in mind, then you have to find a way to use the relationships you've generated to solve your problem. Hopefully they will. This one does. So T1 equals 200 over cosine 40. I don't know what you get, 200 something, right? Well, I don't think it's going to be negative. 261. Yeah, there we go. Yeah, 261. Now, once I have that, and don't forget, guys, we deal with degrees in here. I'm going to plug that 261 here to figure out what T2 is. Anybody got T2? Yeah, 168. So I buy a 200 Newton sine. I go to the hardware store and I buy cabling, and the cable only withstands 200 newtons because that's all my sine weighs. Is that going to work out for me? No, but people do that kind of stupid stuff all the time. They don't think about the fact that physics probably has something else. Why would I want to even do it this way? Why not just hang it with a 200 Newton cable? It's real simple, stability. By putting the two cables here, I add tension to the system so the sign stays in place and doesn't swing around. That's why you would make choices like that. But it means you have to get cabling that's more durable than the actual weight of the sign. You have to mow the lawn, so you apply a force along the handle of the lawnmower. The handle makes an angle of theta with the ground. When you are operating the lawnmower moves at a constant speed in this direction. Can you identify all the forces acting in the system and generate a free body diagram that could be used to analyze the lawnmower? All right, so did you reduce the lawnmower to a dot? Did you decide from the beginning that the net force is going to be equal to 0? All right, did you begin the process of drawing arrows that represent the forces that are acting on the lawnmower?
Yes.
All right, name a force that acts on the lawnmower. Gravity is a good one. Let's hit that one first. So gravity is acting downwards on the lawnmower. Look, be the first one to say gravity. It's the one that's always going to be true. So the weight of the lawnmower. What's another force acting on the lawnmower? Go ahead. That's a common mistake, but the speed isn't a force. Okay, so the speed is actually what's happening to the lawnmower because of all these forces, but the speed wouldn't be drawn on a force diagram because only forces can be. So it's going to be gravity, contact forces, or resistive forces. It's going to be one of those. Go ahead. Friction. How would I draw friction?
Backwards and against the constant speed.
Sure. I would have to draw a force this way that represents the frictional force. It has to be parallel to the surface and opposes the direction of motion of the lawnmower. So this is all that grass and stuff scraping against the bottom of the lawnmower body. And I'm going to label it kinetic friction because the lawnmower is moving. So effectively the bottom housing of the lawnmower is sliding against the bottom of the ground. And the other forces acting? Go ahead. Okay, so a normal force on the lawnmower. So I will draw an upward force because it has to be perpendicular to the surface. And you'll note I'm going to draw this force greater than the weight. Did you guys do that? Because I know that I'm pushing downwards on the handle. And I need to make sure I have something that shows balance. So I know there's weight going downwards, but because I'm also pushing downwards on the handle, I expect that the ground is actually pushing upwards more than just the weight of the lawnmower. And anybody who's ever had to push a lawnmower knows the heavier the lawnmower gets, the harder it is to push the lawnmower across the ground. So you tend to lift up on the handle when you reach hard to reach places or hard to mow over places. But since all of you have self-propelled lawnmowers, you may never have encountered that. Good, regular, good old push mower. Now, when you're drawing this one, remember, you want to align with with your handle, but also you're trying to make it so that this is equal to this, and you have two downwards forces here balanced by one upwards force here. How did you guys label this force? Did you name it something? Go ahead. Okay. Normal force of a push. Actually, it would be okay if you just said push or FP. You will sometimes be given forces that you just have to use that don't necessarily fit into a category. As long as you create a label and stick to it, you'll be fine.